A quite famous physics experiment in history is Rutherford's gold foil experiment, which led to the discovery of the nucleus. Basically, Rutherford had an alpha particle emitter. An alpha particle, at the time it was not known, now we do know it's two protons and two neutrons combined. It's the nucleus of a helium atom, two protons, two neutrons. So it has a positive 2 charge, or a positive 2e charge. And they travel somewhere in the vicinity of 5% the speed of light, 0.05 c. All they knew at the time was that it was radiation, and so they had alpha radiation is what they called it. So he used a alpha particle emitter, basically a radioactive substance enclosed in a lead box, and then he put a hole in it, spot that the alpha particles could come out. A detector screen around the outside, more than likely, I believe it was made of some sort of phosphor material. That way when an alpha particle hit it, it lit up. A thin piece of gold foil. The reason gold was used is it could be hammered really, really thin, meaning that there wasn't extra thickness to it to where the alpha particles might hit something else. In other words, he was able to get it as close to a atom or a few atoms thin as possible. That is one of the unique properties of gold. It's very malleable, yet still will hold together. So he shot alpha particles at it, and he expected, according to the current theory, so-called the plum pudding model is what we call it now, where you have this sphere of positive charge, like the positive charge is a goo laid out throughout an atom, and then these, what we called plums, negative charges, electrons, kind of spread throughout it. He expected that all the alpha particles, which he knew had a positive charge, would just stream right on through unaffected. Instead, what he found is most of the alpha particles streamed right on through unaffected and just came out the other side straight through, but occasionally some were deflected off at angles, and occasionally they actually reflected back or straight back. So sometimes they reflected right back, and the explanation for that was there must be a positive charge in a nucleus. All that positive charge must not be spread out as a goo all over the atom, in other words, like a positive sphere with just electrons scattered throughout it. All that positive charge must be contained right in the center, the nucleus of an atom. So his gold foil experiment proved the nucleus of the atom. So we're going to actually do that problem. I have here an alpha particle traveling at 5% the speed of light, and it's going to go towards a gold nucleus, so 79e, 79 protons inside of gold. And if you think about this in terms of conservation of energy, it has a very high energy whenever it's very, very far away at an electrical potential of practically zero. Very, very far away is going to be like a infinite distance, okay? So an electrical potential of zero. And as it gets closer and closer and closer, it's going to transfer that potential, or that kinetic energy found in the velocity into electrical potential energy, and eventually all of the kinetic energy will be transferred into electrical potential energy at some distance d away from the nucleus. Here, your velocity will be zero, and we'll have some high electrical potential. So I want to solve for how far, what distance away from a gold nucleus would an alpha particle going 5% the speed of light finally stop and then turn around and reflect back off. To solve this problem, let's kind of label our picture a little bit here. A long ways out, at least a long ways compared to the size and charge of an atom, the initial electrical potential, VI if you will, is zero, and we have some large kinetic energy. And that kinetic energy we can calculate using 1/2 mv squared, right, being V there being initial velocity. Because we know the mass of an alpha particle, 2 protons, 2 neutrons, and we know its velocity 5% the speed of light. Now, whenever we get some distance d away from the gold nucleus, all of this kinetic energy has been transferred into potential, and even more specifically, into electrical potential, some V that we're going to try to calculate, and at that point in time, our kinetic energy is zero. So all of my kinetic energy gets transferred into potential, more specifically electrical potential. And once I calculate this final electrical potential, right, whatever that final electrical potential it stops at, I can use my equation, electrical potential equals K, big Q being the charge it's producing our electrical potential, aka the gold nucleus, 79 times the charge of a proton, divided by R, and solve for R, the distance away that this electrical potential is at. So let's go about solving. So what we can say here is all the kinetic energy that we lose, thus the negative sign there, is going to be transferred into, and let's put a delta, a delta Ke. So all the kinetic energy we are going to lose is going to be transferred into potential energy. So negative 1/2 MVI, because MVF there is 0, if you want to kind of see that a little bit fuller there, 1/2 MVF being final velocity, right? And our final velocity is nothing there, so this part goes away, leaving negative 1/2 initial velocity squared, is going to equal the change in potential energy. So the change in kinetic equals the change in potential. So that our negative sign here came because the final is 0. Is going to equal my change in potential. Well, I know everything that I need to know here because I know the mass of a proton and a neutron, which an alpha particle is made up of 2 protons, 2 neutrons, helium nucleus. So every time you see alpha particle, 2 protons, 2 neutrons, and I also know its initial velocity was 5% the speed of light, and that guy is squared. So now let's actually translate this into numbers here. Let's substitute in what the mass of the proton is, mass of neutron is, and the speed of light 3 times 10 to the 8th. Now, the mass of a proton and a neutron are almost the exact same thing. In fact, so close that your AP packet only reports it with 3 sig figs, reports it to be exactly the same thing. When we get into nuclear physics, we're going to need to use more specific values. But for here, we can use the same mass for each of them. So sometimes you'll hear this called a nucleon mass, and here's the speed of light. And I come out with 7,515 times 10 to the negative 13th joules is the amount of potential energy I gain. I actually made a little math error up here. This negative, right, is in front of the kinetic energy. I'm losing kinetic energy. Amount of kinetic energy lost is going to be the amount of potential energy gained. So that negative should be out in front here. That negative should be out in front here, right? So negative times a negative equals a positive, right? So negative out in front over here, meaning that I come out with a positive gain of potential energy. Just think it through conceptually. I am losing kinetic energy. I am gaining potential energy, a positive 7.515 times 10 to the negative 13th joules. Now I can take that potential energy that I just found, substitute into my equation. Change in electrical potential is equal, or electrical potential difference is equal to change in potential energy divided by Q. Now, change in electrical potential, remember, is going to be your final electrical potential minus your initial electrical potential, delta U over Q. And my initial electrical potential over here is 0. So I've just got my, because I'm coming from basically infinitely far away. So my final is going to equal delta U over Q. And Q, I know, it's going to be the charge of an alpha particle. Now, the alpha particle has four subatomic particles in it, 4 nucleons. It's 2 protons and 2 neutrons, and neutrons don't factor into charge. So the charge of my alpha particle will be 2 protons. Whenever I substitute those numbers in, I come out with my final voltage is going to be 2,348,437.5 volts, and I rounded a little bit here. So thinking this through once again, I had a bunch of kinetic energy of this alpha particle coming in towards my gold nucleus, right? All of that kinetic energy was converted into potential energy, U, right? And so I calculated the total kinetic energy getting converted into the potential energy U. Then I was able to calculate what electrical potential difference that would be, and since the initial is 0, I'm able to calculate the final electrical potential that this alpha particle will end up at, aka the final electrical potential right here. So now I know that, I can substitute into this equation and solve for R. So whenever I solve around for R here, right, multiply R to the other side, divide my volts, the 2,348,000 over, right, I come out with a distance away, d, or a radius away from the gold nucleus, of 4.8 times 10 to the negative 14th meters. So this alpha particle is moving so fast, it has to come really, really, really close before it's going to turn around and shoot back, before finally the force becomes so large that it decreases the velocity at a fast enough rate, decelerates it fast enough that it brings it to a halt and turns it around and shoots it right back. Now, a gold nucleus has a diameter of somewhere around 1.4 times 10 to the negative 14th meters, or 14 femtometers, femto meaning times 10 to the negative 15th there. And you have to get, quite evidently, very, very close to it for the force to be large enough to turn it around. So that explains why the vast majority of electrons in the gold foil experiment kept going straight through. The atom is made of mostly empty space, with a very, very small, dense, positive nucleus there. So since you have to get very close to a very small nucleus for the force to become so large, turn it around, the odds of doing that are very low. Now, obviously, if you pass somewhere close to it, you're going to get a little bit of force and get deflected. But still, the vast majority of space of an atom or the vast majority of the area an atom makes up is empty space going from the nucleus out to the electron.